In this video, we're going to be talking about different types of FRFs, the 3 or 6, depending on how you look at it, types of FRFs. Now, if you haven't seen my other video on FRFs, you should pause and go watch that because I think it would be really helpful. This video sort of builds on that other video. So I'm going to do a little bit of review before I jump right into it. We have our original single degree of freedom system. We have a mass M, a stiffness K, and a damping C. We have a force being applied, that's F, and the amount of displacement it's moving is X. I'm going to redraw that receptance equation, and this is an FRF, a frequency response function. It is calculated by taking the displacement X over F, or an output over an input, which is all an FRF really is. It's just a measurement of output over input. Now this FRF is called receptance, and it was generated using this equation. The values that I put in for this equation are going to matter later because we're going to kind of find them again when we're looking at our different FRFs. So I want you to keep these in the back of your mind. The stiffness value for this system is 4 times 10 to the 6th newtons per meter. The damping value is 500 newton seconds per meter, and the mass is 10 kilograms. Those are the values that I use to generate this FRF. Some more quick review. Let's redraw this receptance plot. We have a natural frequency, which is that little resonance up at the top. This is the location where our displacement response is higher even though we're putting in the same amount of force. So our structure is shaking or resonating. This can be calculated by taking the ratio of the stiffness to the mass of whatever your system is. So we can calculate this using omega n is equal to the square root of k over m, where omega n is the natural frequency in radians per second. But typically we like to look at things in hertz. So if we were to calculate this out for the system using numbers that I have already given, we would end up with a natural frequency of 632 radians per second. Now, if I want this in cycles per second or hertz, I can just divide out by 2 pi and you'll see that the natural frequency for this system is 100 hertz. And that sort of makes sense. Might have chosen these numbers on purpose to make it a nice round 100 hertz value. But the peak of this is occurring at 100 hertz on the frequency plot. Now there are 3 different zones of an FRF that we're going to be going over, and these are going to be really important today. There's the yellow stiffness controlled zone, the red damping controlled zone, and the blue mass controlled zone. So we know what a receptance plot looks like, and if you watch the other video, you've kind of got a sense of why these different controlled zones are what they are, but I want to take a look at the FRF upside down. So if I flip the output and the input, now you'll notice that my FRF is upside down, and you should also notice that my axes have changed. I now have F over X, and what you can do with this graph is you can pull out the stiffness. We have flipped it upside down, and K can be found by finding that stiffness controlled portion, that flat line. It'll be equal to 4 times 10 to the 6th Newton per meter. And that checks out with the values that I entered in to create this FRF. And this FRF is called dynamic stiffness. And I think that's a good name for it because it gives you the stiffness value for that system. Now, if you are wondering where this value comes from, you'd have to go back to the original equation. This is the equation used to generate the dynamic stiffness graph. And what we can do is that flat stiffness portion occurs in the low frequency range. So let's assume that our frequency is equal to 0 or very low, omega is equal to 0. And look what happens when we multiply these terms out by the omega values that are attached to them. They end up canceling and you end up getting K. At very low frequency values, your FRF is equal to your stiffness value. And it's sort of the same idea for the rest of the FRFs we're going to talk about. Now, if we take the derivative of displacement, maybe we didn't measure displacement, maybe we measured velocity, we could plot that as well. And now we would have x dot, or velocity, over the force. That's still an output, velocity is, and the force is still an input, but our equation is going to look a little bit different. It's going to look something like this. The equation we use to generate it is this now. Now, when we're in the frequency domain and we're trying to take the derivative, all we need to do is multiply by j omega, where j is that imaginary number. You could also use I if you wanted, and we're gonna see what that does when we're looking at the complex plane multiplying by j. But all I'm doing right now is I'm taking the previous equation and I'm multiplying it by j omega. So I'm taking the derivative. So if you take the derivative of displacement, you get velocity, and I get a plot like this. And this plot is called mobility. One unique thing about this plot is it gives us a really good idea of what's going on at the natural frequency. If we were to flip this plot upside down, now we have force over velocity, our equation is going to look like this. Our graph's called impedance. Now what we can do with this graph is we can find our damping value. So on the impedance graph, the damping value is actually here. On the mobility plot, it's 1 over c. But if we flip it upside down, it's just c, and it occurs at the natural frequency. And this is a really cool phenomenon that I think gets illustrated better once we look at complex planes. But this is one nice thing we can do with the impedance graph. Now, if we wanted to derive again, maybe we measure acceleration, and that's very common. A lot of people use accelerometers to measure acceleration. We would take the derivative again. So now on the axis, I've got x double dot, which is the acceleration over the force. It's still an output over an input. Our graph would look something like this, and our equation's changed again. And all I've done from the previous step is multiplied by an additional j omega term. This is called the accelerance, and for a good reason. It's calculated using the acceleration instead of the velocity or the displacement. Now this one, if you're keeping up with the pattern, also has a value that you can take off of the graph. But what we'll do is we'll flip it upside down. Now we're dealing with force over acceleration. If we graph it, it'll just look flipped. The new equation will look like this, and we'll call this dynamic mass. And I'm sort of giving it away here, but the straight line at the end is where we can pick out that mass value. So let's plot these FRFs, and one thing I've sort of neglected to mention kind of on purpose is that these FRFs are complex values. They have a real component and an imaginary component, and all I've showed you so far is the amplitude, which is just a combination of the real and imaginary component. What I've sort of neglected to mention is that these have a phase. The phase comes from that imaginary portion in the equation, and it's calculated by the arctangent of the real portion and the imaginary portion. The phase is really important because it can help you find the natural frequency. So if I were to find my natural frequency, I'm aligning my cursor, it's at about 100, and then I look at the phase portion, I can see that this cursor crosses at about minus 90 degrees. And that's about what I would expect for a receptance plot. This is going to change as we change these out for mobility and accelerant. So there's a couple different things I could do. I could either drag in this mobility plot, but I think it's actually more interesting and more useful to look at this by just taking the derivative. So if you remember that the receptance is displacement over force, if I want to get to mobility, that's velocity over force, I would just take the derivative. So that's what I'm going to do. I'm just going to right click here and I'm going to single derive on this x-axis. And now, although it says receptance, I have something that looks like a mobility plot. And just to double check, I can take this processing off and drop this in, and we'll see that those graphs are exactly the same. So all I've done between these two is I've taken the derivative by multiplying by that j omega term. Now, while looking at the mobility plot, I want to see where the crossing happens at this natural frequency. I can scroll all the way up and see that it happens at about 0, which is what I would expect for the mobility plot. One really important thing about the mobility plot, and we're going to go on to see this when we look at the complex plane and the imaginary plane, is this is the plot that really gives you some information on the natural frequency. The Nyquist plots will show us how we can pull damping out of the mobility plot. Now let's take a look at the accelerants. I can take the derivative again by going to processing and this time differentiating one time down from mobility, and now I have an accelerants plot. Even though it says mobility, we've just taken the derivative. And we can double check this, once again by taking the processing away and dropping in accelerants. So now we have an accelerants plot, and the way I can tell it's an accelerants plot is because I have this flat portion of the graph at the end in the mass controlled zone. Remember, the accelerants plot is where we pull out our mass value. So it would make sense that the flat portion where we pull this value out occurs on the accelerants plot. Now, if I look at the phase where this crosses now at the natural frequency, I'll see that I have gone up another 90 degrees. It crosses at about 90 degrees. Now, if you're clever, you'll kind of have an idea of why that's happening. We are multiplying by that j, which is the same as imaginary I. You could use I if you wanted to. It's just the imaginary number I. And when we're doing that, the imaginary number I lays on the 90-degree imaginary portion of the complex plane. So as we are multiplying this, you should be seeing this phase rotate about 90 degrees. And I think that's going to be really apparent when we look at these Nyquist plots. So a Nyquist plot just shows the imaginary portion and the real portion. So what I'm going to do really quickly is I'm going to plot the receptance. And you can see I've got a circle, which is what it should look like because I'm plotting real versus the imaginary portion. So this will not look like our sharp FRFs with a resonance, like I showed earlier. Now if I drag in the mobility plot, all I've done now is I've differentiated by multiplying by j omega. What I should see is it rotating 90 degrees. And I'll do that again, and you can see this rotating 90 degrees again. Now this is really nice because now we can see for sure that we know that we're kind of calculating the correct thing. But it's also nice because if I go back to mobility, there's a bit of a trick you can do here on these Nyquist plots, but only with the mobility for damping. So the diameter of this circle, this beautifully plotted circle, is inversely proportional to the damping. If I wanted to pull the damping value for this FRF off, what I could do is add a double cursor. I'm going to add it here, and I want to get the diameter of this circle. I'm going to do the best that I can. So these bounds can be hard to calculate, but that's okay. If I go to calculations, axis range, now I can see that my axis range is 2e to the minus third. Now we said it was inversely proportional, so if you took 1 over this number, you would get about 500. Now if you remember, that was actually the damping value that we programmed into these FRFs that I mentioned earlier. So this is an easy way to pull out the damping values. Now I want to take a look at the inverse FRFs, the ones that we pull other values off of. So I'll leave this behind for now. We'll come back to here, and I'm going to go to my inverse FRFs. And now let's take a look at dynamic stiffness. And if I have dynamic stiffness here, I've got the flat portion once again in the stiffness controlled portion of the FRF. Even though it's upside down, the flat line is here. So if I take my cursor and I kind of click and drag somewhere along this flat line, I can see that the value is 4 times 10 to the 6th. That is the stiffness controlled value from our graph. I mentioned that earlier when I was generating these FRFs. So that's how we pull the stiffness portion out. I'm going to drag my impedance now over, and I can see that this is the impedance graph. There's no straight lines on either side, which I would expect. And to get the C value, that damping value, it's going to occur at the natural frequency. So if I click on this data, my cursor shows that it occurs at around 500, which is good. That is what I entered in for the damping value for this graph. And then let's take a look at the dynamic mass. I can click and drag this in here. I've got this flat portion of my FRF. I want to find where the mass is. If I click on it, I can see that the mass is 10 kilograms, and that checks out with what I had entered in as well. So if you ever forget which FRFs are related to which values, I like to take a look at our equation of motion. So we have F equals mx double dot, which is the acceleration, plus cx dot, which is the velocity, plus kx, which is the displacement. Now, if we look at our accelerants plot, we have x double dot, which is the acceleration over f. We're going to get our mass value, and you can remember that pretty easily because the mass value is tied to the acceleration value in our equation of motion. And if we look at the mobility plot, we have x dot, which is the velocity, over f, the force. We can get the damping value, and that's tied to the velocity in our equation of motion here. And then lastly, we have the stiffness, and I think you have an idea of what's coming. It's calculated by the displacement x over f. The k value can be found here, and we know that we're looking for the k value because it is tied to the displacement in our equation of motion. So I hope that this was an informative video and you gained a deeper understanding into the different types of FRFs and what you can do with them. And I hope to explore more in depth these ideas in the future.